All right, so in this section, we're going to be solving quadratic equations by graphing. And just as a review, a quadratic equation is a nonlinear equation that can be written in standard form, ax squared plus bx plus c equals 0, where a does not equal 0. We've already talked about solving these types of equations by factoring. This entire chapter is going to focus on solving quadratic equations, and this section is going to focus on solving them by graphing. So what we're going to do, basically, is we're going to get our quadratic equation equal to 0, so our standard form equal to 0, and then we're going to graph the function y equals that, whatever we had, ax squared plus bx plus c, and then wherever that y value is 0 on the graph, those x values are going to be our solutions to our quadratic equations. Those points are the x-intercepts, so when we find the x-intercepts, then we have our answers. All right, so for this first example, we're going to solve a quadratic equation that has two real solutions. And we see that we have the equation x squared plus 2x equals 3. So the first thing we're going to want to do is get this in standard form and set it equal to 0. So all I'm going to do is subtract this 3 on both sides. So I'm going to rewrite this as x squared plus 2x minus 3 equals 0. And now this is going to be much easier to solve. So the next step is I'm going to graph the function y equals this expression right here. Okay, so y equals x squared plus 2x minus 3. And then after we graph this, we're going to find when this y value is 0, and those corresponding x values will be our solutions to this equation. Okay. Now, after we do this, I'm going to show you how an easy way to do this on a graphing calculator like Desmos, but it's also important to know how to do it by hand without a calculator. So anyway, the first thing we do to graph a function like this would be to find the vertex, and we know the vertex, the x value of the vertex for any quadratic function is just x equals negative b over 2a. So I'm going to plug in 2 for b here, so it's going to be negative 2 over, and then a is just 1 because there's no coefficient, so that's going to be 2 times 1, and then the 1 I can ignore, and then negative 2 divided by 2 is negative 1. So now I know that the x value of my vertex is going to be negative 1, which means when I make my table of values, that value is going to be in the middle. So I typically like to have at least 5 points when I graph my quadratic functions here. So x and y, so negative 1 is our middle point, and then I can fill these points up. So this will be 0 and 1, negative 2 and negative 3. And what we can do here is, because these values will be symmetrical around the vertex, I only have to solve for 3 values in this table, and that will give me 5 points. So first I'm going to solve for my vertex point here, so negative 1. So I'm going to plug that into this equation. Now I'm going to rewrite this equation down here. Y equals x squared plus 2x minus 3. So anyway, I'm going to plug in negative 1, so that's negative 1 squared plus 2 times negative 1 minus 3. Negative 1 squared is 1. And then we get negative 2 and then negative 3. And I'll scroll down a bit. 1 minus 2 is negative 1. And then negative 1 minus 3 is negative 4. So this y value is negative 4 when x is negative 1. All right, so I can do the same thing. Now, 0 is the easiest number to plug in my opinion. So if I plug in a 0 here, this x term will go away, and then this 2x term will go away, and all I'm left with is negative 3. So I can just put negative 3 here, and since this is the same distance, this x value is the same distance away from this one, this y value is also going to be negative 3. Okay, so now what I'm going to do is I'm going to plug in 1 to our function. So I'm going to get y equals 1 squared plus 2 times 1 minus 3. This becomes 1 plus 2 minus 3. And then 1 plus 2 is 3. 3 minus 3 is 0. So this will give us 0 when x is 1. And now we actually have our answers before graphing. The process of graphing this has helped us find our answers. Because remember, we're trying to find when this equation equals 0 and those x values. So those x values are going to be 1 and negative 3. But let's make the graph just to show you what it looks like on the graph. So to make the graph, I'm just going to plot all of these points. So the first ordered pair that I'll graph is a vertex, which is negative 1 comma negative 4. And then the next one is 0, -3, and -2, -3. And then the next one is 1, 0, and -3, 0. And then I can sketch my parabola through these points. I like to sketch it because if I try to do one smooth curve, it would look terrible. All right, so there's a very rough sketch of this parabola, but we see that the points that when y is equal to 0, we have x equals 1 and and x equals -3, sorry, for when y equals 0. So those are my two solutions to this equation. The answers are x equals -3 and x equals -1. Those are the two x values that make our y value 0 and that make this initial quadratic equation true. I'm just going to show you guys what this looks like on Desmos if we graphed it not by hand, let the graphing calculator do it. So I'll turn on this function. This is our function right here. And then we see that the parabola is crossing the x-axis when y is 0 at the point 1, 0 and -3, 0. So if you're allowed to use Desmos, it is much easier and much quicker to do it. But once again, sometimes you won't be allowed to use it, and you do need to know how to do it by hand. All right, in example 2, we're going to solve a quadratic equation that has one real solution. So we're going to solve the equation x squared minus 8x equals -16. And we're going to do the same process. We're going to get this in standard form, so I'm going to add 16 on both sides. So my equation is going to be x squared minus 8x plus 16 equals 0. And now, once again, I'm going to graph y equals this expression. So I have a parabola that I can graph. So y equals x squared minus 8x plus 16. And we want to figure out when this is equal to 0. So we'll graph it. Once again, we'll find the vertex x value, which is going to be x equals -b over 2a. Negative b, well, b is -8 here. So negative b is going to be +8 or -8. But when we have double negatives, it turns to a positive. And then 2 over 2a, well, a is 1 here, so that's just over 2. So +8 over 2 is equal to 4. So that's my x value for the vertex. So now I'm going to put this 4 value in the middle of my table. Once again, I like to use 5 points. So I have 4. And then to figure out my other points, I'm just going to do 5 and 6, and then 3 and 2. So now I'm going to rewrite our function down here. Y equals x squared minus 8x plus 16. And if I plug 4 in, that will give me the y value of the vertex. So if I have y equals 4 squared minus 8 times 4 plus 16, I get y equals 16 minus 32 plus 16. Well, if I add 16 and 16, that gives me positive 32. And then when I add this negative 32 here, that cancels out. So this is actually going to be 0. And if my vertex value, my vertex y value is 0, that means it's going to be the only 0 because there's not going to be any points that are symmetrical with that. So anyway, I am going to figure out the rest of this graph so I can properly graph it. But we technically have our only one solution right now, which is just going to be x equals 4. But I'm going to plug in 3 and 2 for this function so I can get my symmetrical table filled in, and then I can make my graph and show you what that looks like on a graph. So anyway, I have y equals, I'll do x equals 3, so 3 squared minus 8 times 3 plus 16, and I get y equals 9 minus 24 plus 16. And then I will do 9 minus 24, which is negative 15, and then negative 15 plus 16 is y equals 1. So I get 1 here, and then 1 will also be here as well. And I'll do the same thing for x equals 2. I get y equals 2 squared minus 8 times 2 plus 16. So this becomes y equals 4 minus 16 plus 16. So these cancel out. So all I'm left with is this 4 here. So I can just plug the 4 in here and here. And then I will plot this table on my graph and show you what this graph looks like. So I'm going to start with my vertex. I have the point 4, 0, so that's right here. And then my next point is 5, 1. So graph that here, and then I'll do the symmetrical one, 3, 1. Then the last one I have on this table, last pair, is 6, 4, which is right here. And then 2, 4, which is right here. Okay, and I'll draw my parabola. Sketch it out, I mean. And right here, we see that this point touches the x-axis, but it does not cross, it does not go through the x-axis. There's no negative y values here. So 0 is the minimum point, which is why there's only one solution. So anytime that our vertex is touching the x-axis, then the number of solutions we're going to have is just 1. And that's going to be the x value of the vertex. So our final answer that makes this equation true, I'll write it down here, is x equals 4. Because when we plug this in, it makes the equation true, and that is the x value of our vertex. Now to graph this function on Desmos, I'll show you guys what it looks like. So I'll type in the function y equals x squared minus 8x plus 16. And we see right here that this point is just touching the x-axis, and there's no negative points, so it looks just like our graph. So once again, if you're allowed to use a graphing calculator, this is a much easier way to do it, but it is necessary to learn by hand as well. All right, so for example 3, we're solving a quadratic equation with no real solutions. So we're given the equation, negative x squared equals 2x plus 4. And there's actually multiple ways to do this. There's technically multiple ways to do all of them, and I'll show you the 2 ways that you can do it here. The first way that I'm going to do it is just the regular way. Okay, so I'm going to get all of my variables onto one side and set it equal to 0. So here I'll add x squared. And then I get 0 equals x squared plus 2x plus 4. And then I'll set y equal to this so we can graph this function and then see where it crosses the x-axis. So this function is y equals x squared plus 2x plus 4. So when I graph this one, y equals x squared plus 2x plus 4, we see that there's actually no place where this graph crosses the y-axis. So when is this equation equal to 0, x squared plus 2x plus 4? Well, we have no real number that we can plug in for x that makes this touch the y-axis, makes it equal to 0. So our answer is going to be no real solutions. So there's no real solutions. And the reason why we say there's no real solutions is because in Algebra 2 you'll learn about something called complex numbers, and you could have a complex solution to here. Well, actually you will have complex solutions here, but for now you don't need to worry about that. The answer for this is just no real solutions. Now the other way that you can do this is, instead of getting all these to one side and graphing one function, really, you could just graph both functions. Now we've done something like this before. Okay, so up here I'll write that as, let's say we want to graph the function y equals negative x squared, because that's the left side of this equation. And then I want to graph the function y equals 2x plus 4, because that's the right side of the equation. So this is just a system of equations, except for one of them is nonlinear. So now I'll graph those two equations in Desmos. And I have y equals negative x squared as my first equation, and then y equals 2x plus 4. And we can see that this line and this parabola are never going to intersect. So the equation over here is saying basically when is this true and this true at the same time? And the answer is never. It's never in our real number system. We don't have any real numbers that we can plug in that will make this line intersect with this line. Okay, so that's another reason why the answer to this question is no real solutions. All right, so now the instructions say for us to find the zeros of the functions. So recall that a zero of a function is an x-intercept of the graph of the function. So when we're looking to find the zeros of the function, the x values that make the function 0, I just look at the graph here. So if I look in at the graph, I want to find where this graph crosses the x-axis, aka where the y value of this graph, or the f of x value of this graph, is equal to 0. I see one here, here, and here. So I'm going to draw those points in right now. One right here, here, and here. And let's just figure out when those values equal x. So this one is -1, so we get x equals -1. This one is +2, and then we have +3 here. So we have x equals -1, x equals +2, and x equals +3. So my zeros are just these x values. X equals -1, x equals 2, and x equals 3. Now, to make sure that these answers are correct, you could plug each one of these into our function and make sure that our y value, or our f of x value, would equal 0. But all you need to do to find our zeros here is just look at the graph, see where that graph crosses the x-axis, and figure out what those specific x values are. And then you're done. All right, so now for example 5, we are approximating the zeros of a function. Okay, so the graph of f of x equals x squared plus 4x plus 1 is shown. Approximate the zeros of f to the nearest tenth. So we're assuming that we would not have access to a graphing calculator, which would tell us the exact value. But we can look at the graph here, and we are given the function. So here's the graph, and I see that these red points are my zeros of this function, okay, the x-intercepts. So I can see that one of them is in between -4 and -3, and it seems closer to -4 than -3. And then this one is in between 0 and -1, so it seems closer to 0, okay? So I'm going to use that, and then I'm going to use a scientific calculator to estimate. I know one of my zeros is in between -4, and I'll call my zero x, and then -3. Okay, so now this is where I can do some guess and check. And the instruction said we want our zeros to the nearest tenth. Okay, so what I'm going to do is I'm going to go on the calculator, and I'm going to guess some numbers into this function that are in between -4 and -3. So because, like I said, this seems closer to -4 than to -3, I'm going to guess a decimal that's closer to -4 than -3. So I'm going to say, I'm going to guess -3.6 at first. I'm going to plug this into the function. So I'll do -3.6 squared, and then plus 4 times -3.6, and then plus 1. And this gives me the value -0.44, which is very close to 0. So -3.6 is close, but it's still negative. This is a negative value. So I'm not going to be certain that I have the closest one until I find the closest tenth that is below and the closest tenth that is above. Okay, so I'm just going to write that f of -3.6 is equal to -0.44. Okay, so now basically this is a little too low. So now I'm going to try one higher. So that's going to be -3.7, and we'll see what that is. So I'll just change this, -3.7 and -3.7. And now I get that when I plug in -3.7, our answer is -0.11. So that's even closer, but that's still negative. So I write -3.7 equals -0.11. So now I have to try one more, which is 1/10 lower, so -3.8, which I'll plug that in right now. I'll just change the 7 to an 8, which is one of the reasons why I love using Desmos' calculator. It's a great tool. All right, so now I get 0.24. So this is equal to, and I notice that this is slightly off the screen, so I'll move this over. So this is equal to 0, let's see, what did it say? 0.24. All right, so now the next one is, this is positive, but this is not as close to 0 as this one. So our estimate for this 0 is going to be -3.7. So one of our x values is about, I should say, -3.7. And now I'm going to do the same thing for this point. And luckily I have my function form right here, so all I have to do is plug in some numbers that I think. So I think this is much closer to 0 than to -1. So I'm going to guess maybe -0.3. And since this is since I can kind of tell that my vertex is the x value of my vertex is -2. Negative 0.3 is the same distance away from -2. So I'm going to try negative 0.3 and see what happens. I'll plug it in here as well. And I get negative 0.11, which is no shock that it's the same value. So this is going to be f of negative 0.3 equals negative 0.11. Okay, and I am certain that this is going to be the answer because this is the symmetrical one here. And if this is the closest estimate on the left side of the axis of symmetry, then this one's going to be the estimate on the right side. This is a negative value, so we do need technically a positive value. So I'll plug in one higher than this, which is going to be negative 0.2. And when I change that over in the calculator, this becomes a 2. And then once again, I get my positive value of 0.24. And so I know for a fact that this is the closest one now. So now my other x value is equal to negative 0.3. So these are the two closest approximations of the zeros to the nearest tenth. All right, so for example 6, we have a football player kicks a football 2 feet above the ground with an initial vertical velocity of 75 feet per second. The function h equals negative 16t squared plus 75t plus 2 represents the height h in feet of the football after t seconds. A, find the height of the football each second after it is kicked. B, use the results of part A to estimate where the height of the football is 50 feet. And then C, use a graph after how many seconds is the football 50 feet above the ground. So that's a lot, okay? But the first thing that we're going to do is part A. It says find the height of the football each second after it is kicked, okay? So that sounds like we're going to make a table, okay? And then we have the function that we have our table, which is h equals negative 16t plus 75t plus 2. So I'm going to pull up Desmos, my scientific Desmos calculator. And I'm going to have the function in here so we can easily make our table. So it's going to be negative 16t squared and then plus 75t and then plus 2. And it says each second. So I'm going to make my table over here. So this is going to be seconds and then the height. So let's see, we'll start this. So after 0 seconds, I don't even have to plug it into a calculator to know that it's going to be 2 because the t terms are going to be canceled. Okay, and I'm going to change this to t because that'll just be more consistent because t is our variable here. So t is when t is 0, h is going to be 2. Okay, now when t is 1, this is when I'll plug it into the calculator. A 1 here and a 1 here, so I get 61. So 1 second, the ball is 61 feet in the air. Now I'll do 2 seconds. And now it's 88 feet in the air. And then I'll do 3 seconds. And now it's 83 feet in the air. So 383. I'll scroll this down a bit. I'll extend my table. And then for 4 seconds, I get 46. And then I'll do 5 seconds, which is negative 23, which means, so I'll put that on our table, but we'll see what that really means. Would the ball really go 23 feet below the ground? No, it would hit the ground somewhere in between here. Okay, so now I'm going to go full screen again. And we'll scroll up and we'll say, it says find the height of the football after each second is kicked. So we finished part A. Okay, this is our table. We know the height after each second. Okay, part B, use the results from part A to estimate when the height of the football is 50 feet. All right, so the height, this is our height category. We have 2, 61, 88, 83, 46, and then it stops. It's not in the air anymore. So when we want the height to be 50, let's just figure out where that could be. So I see that 2 and 61, well, it would have had to go in. It would have had to hit 50 as it was going from 2 to 61, but it was probably going to be a lot closer to 1 second than to 0 seconds. So the first time it hits 50, it's probably a little before 1 second. So that's the first time that it would go through 50. Then it comes back down, okay, in between 83 and then 46. And then this is also going to be probably closer to this 4 seconds here, because 46 is much closer than 83. So it's going to be a little bit before 4 seconds for our other one. And that is our estimate of part B. We don't really have enough information just given this table to find like a really super accurate approximation, but this is as good as it gets. Find the range and then say which number it's closer to. All right, now for part C, it says use a graph, and then after how many seconds is the football 50 feet above the ground? So basically, we're going to now graph this function, which is right here. We're going to graph this function and then see the exact value when it's 50 feet. Okay. So there's multiple ways to do this. We can just graph this function, right? And then set this h value to 50. So see where this crosses 50. Okay. Or we could plug 50 in and then subtract 50 on both sides and then set y equal to that new function and then see where that one equals 0. But I'm just going to do the 50 version because I think that one's easier for us. All right, so I'm typing in my function into Desmos, but instead of h, I'm going to use y. Instead of t, I'm going to use x, just because that's how Desmos reads its functions. So y equals negative 16x squared plus 75x instead of t, and then plus 2. All right, so this is our function. I'm going to zoom out a bit. It is, and I'm going to change this axis so you can see. So here's our parabola. We see that after 0 seconds, it's 2 feet above the ground, and it goes up and then comes back down. Okay, but we want to know when it is exactly 50 feet. Okay, so I'm actually going to plug. I could just try to check where it's 50, but in order for Desmos to tell me the exact answer, I'm going to just plug in the equation y equals 50, and then see where those intersect. Whenever there's two functions that are intersecting, Desmos will tell us. So if I go right here, it says our y value is 50, our x value is about 0.75. And then over here, we get about 3.923, which do go with our estimates. We said that this x value would be a little bit before 1, but closer to 1 than 0. And then we said this one was going to be closer to 4 than 3. And these are both accurate. But we've used this graph now to find our x values that make this y value 50. So back to the problem, I'm going to write 0.765 is around one of our x answers, which is more exact. And then 3.923 is around our other x answers. So we look back at the question for part C. How many seconds is the football 50 feet above the ground? You know me. Whenever we have a word problem, I do like to answer it with a word answer. So what I'm going to type in is the football is 50 feet above the ground after about 0.765 seconds after the kick and about 3.923 seconds after the kick. So now we've solved our x values from the graph and we've written a word answer, and now we're done with this one.